And welcome everybody to our night of talks, a special night of talks, especially for Engineers Week, which takes place all this week. So it's a week-long series of events by engineers to kind of showcase to society what engineers do and encourage the next generation to take part. So you can go on to the Engineers Ireland website, and there's plenty of events on there for all age groups. We're only about halfway through the number of events now, and there's still plenty of events on throughout the rest of the week. So tonight's, so we have two talks tonight. One on AI from Tomas, and another talk on remote over OTA updates from Sergey. But just a little bit about our co-organisers of tonight's event. So we have Tog, whose YouTube channel you have just joined. Also, we're co-organised by Engineers Ireland's Young Engineers division. So they're a special group for engineers under 35 who organise events and CPD trainings for early stage engineers to help with their career. And a bit about TOG itself. If it's your first time tuning in, TOG is a hackerspace based in Dublin City Centre in the Black Pits. We're closed at the moment, unfortunately, with our level 5 restrictions. But we do all sorts of stuff like 3D printing, laser cutting, crafting, brewing, metalwork. The list goes on of all different sorts of interests our members get up to. At the moment, we're running a number of virtual events. So, for example, every second Wednesday we have a coding night. Next Wednesday, for example, we have a science fiction book club. We have a crafting night. We meet up and help each other and help beginners edit Wikipedia. So we've lots of stuff still going on, even though we're not meeting in person. So the best way to follow along all of our events is either go onto our website, tog.ie, or jump onto meetup.com, and all the events we are hosting now are up there. So we're going to jump right into the talks. The first one is Professor Thomas Ward. I know Thomas a number of years doing science outreach and various maker education programs. Myself, Tomas, and a number of others run the Dublin Maker Festival, which happens each June and July, where we get 10,000 visitors when we have it in person. So Tomas is no stranger to maker sorts of activities, and I think his talk here tonight, I'm sure, will have a little bit of that sprinkled in. So now we're going to jump over to Tomas's talk.
Okay, hello everyone. So I'm calling this talk Faking It in AI because I was word playing around with the phrases fake it till you make it and of course faking it in AI. So my thinking there was fake it till you make it. That reflects a philosophy I'm interested in, a philosophy in engineering innovation that works for me anyway. This idea of imitating competence to gain competence, that sort of thing. I think it's a very valuable mindset that good engineers often embrace, probably maybe subconsciously or covertly, because professionally engineers often need to project quite a conservative sort of, yep, that bridge isn't going anywhere sort of, professionalism and mastery of their art, right? But of course, engineering is all about risk taking. So when it comes to engineering innovation, especially in an area like machine learning or AI, where the half-life of knowledge is something like probably about 12 months or so, you're always chasing competency or flirting with incompetency. So my thoughts on that are just to get comfortable with that. That's where we are. That's the world we live in now. So, embrace that. It makes things exciting. And also the upside, of course, is that there's always an opportunity to go from to break into a new area and to go from zero knowledge to mixing it up with the experts in a pretty short space of time. So on that note, let's move to the faking it in AI bit. So as you probably realize, I'm going to talk about my own team's journey starting out faking it in AI, imitating competency to gain competency. And what makes this interesting is, I suppose, as well, is that a lot of our research ultimately really got into faking it in AI, literally fakes, deep fakes in AI, and how we use that to solve engineering problems. So in 2018, so it's when I started really I was making this little pivot, or quite significant pivot, into kind of deep learning sort of technologies. My engineering team and myself, we would do a lot of work in machine learning anyway, but in our area, our chosen area of brain-computer interfaces. And there, the machine learning, it was, I don't say it was easy, because we're trying to listen, measure signals from somebody's brain and figure out what they're thinking, or figure out if they're might move their left hand or their right hand, for example. But we'd go heavy on the signal processing, or taking the signals from their brain and mathematically being very clever about how we would transform it into features that would be very discriminative, very clear about what they're saying in the brain. And then our machine learning algorithm didn't have to do very much work. It would just needs to see if one or two signals are going above a threshold. It's nearly be just a threshold detection, right? So we put all the work traditionally into the feature processing, or the feature engineering, and left the machine learning pretty light, well, relatively speaking. But we could do good things like this. For example, this nice little project we had, or thing that we developed, nice piece of innovation, where this is a real-time attention monitor. So we're actually working with little wearable headsets here, some of the team that was working with, and we were measuring brain signals. And in this game that we came up with, we were processing the brain signal to focus in on an aspect of your cognition or your mental state related to paying attention, right? Which maybe, hopefully, people are still doing during this talk. I mentioned that because that idea of paying attention and monitoring a person's attention via brain signals is a nice application of machine learning, and something that we're currently doing to look at driverless cars, or blended autonomous vehicles, or blended control of autonomous vehicles, such as driverless cars, where there might be some remote supervision by a fleet, somebody managing this fleet of cars and monitoring their attention, and we call that neuroergonomics, is a cool thing to do, right? So that's one of the applications we're doing of brain-computer interfacing. But my point here is that our machine learning, even though this is a sophisticated problem, the machine learning that we used wasn't that sophisticated. Signal processing was, right? So anyway, when in about 2018, wanted to see what we could do with deep learning techniques and see if there's anything interesting we could turn our hand to. So kicking out from brain-computer interfaces, I thought I wanted to get into, I was thinking, where do we fall short in some of the engineering things we look at? And it's usually in the real world, when we're trying to measure what people are thinking and doing in the real world, which is a noisy place, right? A very noisy, messy place. And the traditional signal processing approaches and engineering approaches we take to try to measure what people are doing, they kind of fall flat in the presence of lots of noise and lots of kind of sources of error, if you like. So we started with something simple. We started with wearables. Now, not brain-computer interfaces or measuring, something sophisticated like that, just wearables like a Fitbit, right? Because wearables are everywhere. And because they're everywhere, we can get lots of data from them. If there's one thing I didn't know about deep learning at the start, that generally they needed lots of data. Well, not generally, they did need lots of data. They do need lots of data. So here was our first problem that we kind of looked at that made us think about where deep learning might be able to help us. Let's look at a Fitbit, right? Let's look at the heart rate signal that might be measured at the back of your Fitbit. It's a little pulsatile signal, like you can see on the screen here. And by counting those pulses in a unit time, you can figure out heart rate, right? That's your heart pulsing away there, essentially. Well, the blood vessels associated with the heartbeat. So now, what's interesting about that with a Fitbit, when the signal looks very easy there, looks nice and clear, but when somebody's maybe walking, right, that sensor is bouncing off their hand. And so you get lots of artifacts. It gets messy. It's a classic example of this messy real world situation I was just referring to there. Look, and then it gets even worse when you're doing more strenuous things. Here's somebody running here on the top right. Somebody's running, the sensor's really bouncing off, and it's very hard to measure heart rate in that situation. Even though I know your Fitbit, it does purport to tell you what your heart rate is when you're running and walking, but it's got its work cut out for it, right? But when we looked at this sort of challenge, classical machine learning on classical signal processing kind of fails. But it's interesting. If I showed you some other this bottom right hand corner here, this is more data from that Fitbit. If I asked you just by visually looking at it, do you think this was when somebody was resting, with no noise on the signal, or walking or running? You might, from looking at it, even though I know it's probably not streaming very smoothly here, you might say that looks a bit like running, doesn't it? That looks similar sort of characteristics. So how are you doing that? How are you making that discrimination, right? You're eyeballing it, right? So we thought, wow, if you can eyeball it like that, is that not what these deep neural networks are getting good at? These convolutional neural networks, this sort of AI that we hear about? And sure enough, it is, right? We looked at Google's Inception, right? Google's Inception is a deep neural network, a convolutional neural network that was really good at working with this kind of classic competition data set, which contains millions and millions of images of all sorts of things. And, cats and dogs and, cars and airplanes and ham sandwiches or whatever, right? Lots of these sort of images. And it was incredibly good at being able to distinguish these things. And when we read about that, we said, that's really cool. I wonder, could we teach it to look at those plots and learn, those heart rate signals, and figure out that this is somebody's Fitbit data when they're walking, and this is when they're running, and this is when they're on their bike or something, right? That'd be cool, right? So rather than be getting upset about the disruption in that wearable signal, we use that disruption to figure out what people are doing and to get a human activity recognition with that Fitbit. So what we did was we took this very complicated neural network. Well, for us, it was for sure, right? It's got many, many layers and so many neurons, and training it must be it's a pain in the neck. But we learned about transfer learning. That's where you teach an old network like this Google's Inception v3, and you just train it a little bit, a particular part of the network, on your data. And so it retains all the knowledge it had on learning cats from dogs, from ham sandwiches, from airplanes, but could then maybe learn whatever idiosyncratic thing you wanted it to teach, that you wanted to learn, such as these images, these time series, these signals. So that's exactly what we did. So we trained the last layer, or the second last layer of that network, and we showed it lots of these Fitbit data signals. And sure enough, it was able to detect whether somebody was walking, running, cycling, or just going for a gentle stroll or cycle with, world-leading accuracy for that particular type of problem. I think it was 92% accuracy we got on that, while the previous result we used in classical machine learning was something like 60%. So we totally faked that. We didn't really. We just had a clever idea of hacking it, if you like, of just doing transfer learning, and that was super. And then I got us thinking, yeah, we're really faking it here, we might make it. And then we saw what else we could do. So check out this. This is an interesting little challenge about, it's related to fakeness.
In tonight's Tech Minute, millions of Americans have Fitbits and pedometers in order to track their physical activity.
But as CBS 4's Gilma Abelos reports, some people have figured out how to earn steps without ever taking one.
This man isn't doing laundry. He's asked us not to show his face because of what he is doing with his company-issued step tracker.
Put the Fitbit in a sock, hour and a half on no heat setting in the dryer, 11,000 steps. Thank you.
He's earning 11,000 steps without moving. As is the case for many employees, his pedometer is linked to company insurance incentives that can lower his payments.
You are now more involved in, well, how much is this bill? How many steps?
Companies benefit from a healthy workforce, and many are rewarding workers with freebies for getting fit. But there's also a growing movement online to cheat the system.
We're starting with 34.
So I don't have time to play all this, right? But look, people are faking it, really faking it with their Fitbits. And So we said, wow, that's interesting. Can we detect that? Can we figure out if you've taken your Fitbit and you've thrown it in the sock in the dryer, or you've given it to somebody else who likes going for runs every day, and they're running around with about 10 Fitbits on their arms, right? And sure enough, that same trick, our little, Google Inception V3, we taught it that. And sure enough, it was able to tell the very subtle differences between different people using their Fitbits. So again, we were able to detect fakes, people faking their the phonies with their Fitbit swapping. So that was a fun thing to do, and that kind of unramped us onto deep learning, because it started with transfer learning and deep learning. I know there's probably a lot here to take in, but transfer learning is kind of a good way to start with deep learning. And there's lots of frameworks like Keras and PyTorch to allow you to kind of very quickly try out some ideas. So after that, we said, faking things really interesting. Let's see where we can go with this. So then we thought more about faking it, and then we started thinking about deep fakes. And here's how that appeared. We're looking at this problem where we're looking at brain signals from newborn babies, and there's algorithms that would look at the brain signals, and we're seeing brain signals on the screen here, and these algorithms can be used for detecting seizures and things like that. But often there's data missing. Data pops off, the electrode pops off, the data's missing, it messes up everything. So that's a problem. What do you do there? So we gave ourselves that challenge, and we said, well, what can we do? Well, around that time, we became aware of deep fakes started becoming a thing. Like all these images you see on the screen here, that dog, that scene, that kind of a butterfly thing, and that burger, they're all fake, right? This is the deep fake stuff that we're beginning to see. So we said, well, could we do something similar? And again, we started very gently by teaching it pictures, transfer learning on a well-known generative adversarial network, right, which is one of the technologies that up until very recently was a leading technology for fakes. And here were some ECG signals. So it's not brain signals, it's heart signals. So it's easier to distinguish. So we use the same concept, right? So for example, if I ask you if you to draw with a marker, what signal is missing there, you probably replicate what you see to the left and right of it, the ECG sort of waveform, the heart waveform. And indeed, we, by using transfer learning on a well-known GAN, was able to do something similar. And that was our first sort of really big result. So a really interesting result, because that's in time series, right? They're in signals from the body. So we were faking physiological signals from the body. And then after that, we got particularly good at it, right? And so now we come up with our own architectures rather than borrowing or transfer learning over somebody else's well-trained network. We developed our own. And this is my work of one of my PhD students, Owen Brophy, who produced a really good result, kind of a leading result. So we're mixing with the experts now on multi-channel time series from the body. So the signals are all coupled, so you can't just fake one of them in isolation. You have to fake them all together, and together they have to be plausible. So this is some work he's done recently. And so I guess it's a kind of a whistle-stop tour there, but that's sort of our journey in a real nutshell, where we started knowing not very much, started on-ramping through existing deep learning technologies and hacking them to make them work for us, till we built up some confidence. And that once we built up some confidence and some knowledge, we were able then to turn that around and be able to develop really new technologies ourselves and actually finally making it. So maybe we'll have a chat about that.
And take it away there, Sergey. You're on screen now.
All right. Thank you, Jeff. I think you can see my screen, so I'm trying to present now. So please let me know if it's not visible. So my name is Sergey. I'm a
Sorry,
CTO
Sergey, you haven't clicked present yet.
Oh, let me see. Present screen. Okay. Is that visible now?
No, it should be on the kind of bottom bar. It'll say present now.
Might not screen. Okay. Let me share just a single window. Just one sec.
No worries.
Oh. Might not screen. Yeah, it looks like I have to enable screen recording permissions. Okay, Google Chrome.
So just bear with us, folks, as we're just sorting out Sergey's technical aspects while he rejoins and shares his screen. But make sure you stick yourself any questions you have down in the chat. And I can see we're all muted. But I think I'm broadcasting my voice now. So, folks, let me just switch back to so you can see me on screen. So I'm back on the screen there. So while we wait on Sergey to rejoin us, have folks been going to any other Engineers Week events? Have you seen any of the coverage on RTE or any other live events? While I wait for the slight delay in your responses. So I did a great air quality workshop there last weekend, first time doing it remotely. Ended up using a lot of nice open source tools for turning a Android phone into a second webcam and using a screen share facility to capture what was on a tablet and then share it remotely with somebody. So it was an interesting take on how to do a workshop where people were gluing things and flashing firmware and all this done remotely. We certainly ran into some challenges about firewalls and virus scanners for people downloading stuff onto it and trying to grasp my head around 14 or 15 different versions of Windows or different operating systems. But we all got there in the end, and I can see some nice new air quality sensors sticking up on the internet. Yeah, Brian just reminded me there, Engineers Ireland are doing a great Meet the Engineer event tomorrow. You can find about it on engineersireland.ie. So it's a great event where you'll get to hear from different types of engineers because there's so many disciplines nowadays, so it can be hard for students or school leavers to really get a grasp of what sort of engineering discipline they want to do. I know a lot of the bigger universities offer common entry to first year, but a lot of the kind of regional universities and colleges don't. So it'll be a great event to kind of get an insight for what, different types. You have your mechanical, your software that I'm involved in. You have new ones that are just coming out, biomedical, renewables, all sorts of different type of engineering. So it's a good event to go along to. And I guess this is what it feels like on a radio show, trying to come up with things to talk about during a dead air moment. So let me just slightly try and multitask, should I say, and see if Sergey has rejoined. He seems to be still disconnecting. Let me rejoin my meeting on my side and see if he is there. Sergey, you're in the other meeting. Okay, let me get out of that one. Jump
All
into
right.
this one. And how is your
Let me
screen
try
share?
now. I think it should work this time.
Okay, give it a go there. And let me put you
Okay.
back on the main screen and let folks hear you. Okay, let me flip back.
Can you see the presentation?
Yes, and I can then see your face slightly to one side, so it's perfect. So let me
All
just get you on the main screen and broadcast out to our audience. And you are now live. Go ahead.
Okay. Thank you, Jeff. Apologies about the hiccup. So my name is Sergey. I'm the CTO of Cezanta, a company incorporated in Ireland. What we do, we develop technology with focus on connected products of Internet of Things. We have a couple of products that we've developed. Most of them are open source. So a couple of them are Mongoose OS. Some people might know it. And Mongoose Library, that is an embedded networking core. So we have like many customers, hundreds of them, big names and small names. And we are proud to tell that a Mongoose Library, the software based on Mongoose Library, runs on International Space Station, serving scientific experiments. So in this talk, I'm going to talk about VCon, which is a framework for the firmware OTA. So for those who don't know it, it's a remote firmware update. So basically, this talk is relevant for people who might be interested to remotely update a firmware on their microcontroller-based devices or projects. So it all started a couple of years ago in 2017 when a customer of ours was working on the ESP32 firmware. And Mongoose OS customer asked for a Z modem support, and which is it was an interesting request. Z modem is the protocol. It's a quite old protocol for transferring data and files over the serial network. And Mongoose OS already had a pretty good support for files, for local file API and also remote file API. So you could do everything with files, either locally or remotely. So we asked what was the reason for that request. It seemed redundant. And the real reason for the request was that the customer had two microcontrollers in their device. So they had ESP32 and basically an old Arduino 8-bit AVR microcontroller. So they had their business logic, their product working on the AVR, running whatever motors and things like that. And they have developed everything on Arduino basically, and they wanted to update that Arduino remotely. So what we did, we asked them, okay, guys, we can help you to move the functionality of that Arduino to ESP32. You'll have only one microcontroller in your project. You'll have no problem with the OTA because Mongoose OS supports OTA. So you'll have like no trouble. And they rejected. So they said, no, we have that functionality so well tested. We invested a lot on this into hardware, so it works like a charm. we don't want to mess it up. So we don't want to move it to the ESP32. We just want to remotely update it. That's it. And later on this year, another customer asks for a Y modem support, which is a variation of Z modem, pretty much asking the same thing, but the target microcontroller was different. It was a STM32 rather than AVR. And then later on, a couple of other customers asked for the same thing. So what they wanted to do is transfer files to their host microcontroller and update it. So what we decided to do, we decided to implement a solution for these guys. So basically to teach ESP32 to reprogram other microcontrollers. So basically, we developed a specialized firmware for the ESP32 that is able to reprogram an attached a microcontroller of different architecture. And also for that, we created a management cloud. So basically, these two worked in together. So below you can see where the developed firmware worked on like different type of ESP32 hardware, like on modules or development boards with different types of connectivity, with Wi-Fi support or Ethernet or cellular. So the later on, we basically summarized what was the main reasons for people not wanting to have everything on one microcontroller. The main reason was that they already have something working and well tested. They didn't want to move it anywhere. What they wanted to do is just to retrofit the OTA capability. That's it. So they just didn't want to touch a working thing. And the other reason was to keep the logics, the business logic of a device and the OTA update logic separate. The third reason was very convincing. So basically, what they wanted to make sure, if they update a firmware, update their MCU, it doesn't break. So that was crucial, because it's very often, and we have like a lot of experience with that, if you develop a firmware on a single microcontroller, the update procedure, firmware update, should be very, very careful and very thought through, because many things could go wrong. It could be bugs in whatever networking stack, could be bugs in configuration, and basically if out of 1,000 devices, say 1 or 2 can just break because of some corner case you cannot predict. So and with this architecture, when you have like 2 separate micros, it's that problem is solved, because if you have a buggy firmware on your target microcontroller, you can just reprogram it the next minute. Later on, we've developed like this firmware, and we even created our own dedicated modules. The next step for us was to bundle these two together in one board. So basically, have a target microcontroller and the ESP module on one board. So we did that, and that is our own hardware, which combines two. So basically, that is you can think about this as a classic Arduino board with the built-in firmware update capability. So it works like this. So there is a secure management cloud with authentication. You log in, you basically see a list of your devices, you initiate, basically choose your new firmware, and click, choose that file, and that it gets updated. Your device gets updated, and this is how the management cloud looks like. And then let me show you in reality how it works. So here I have an Arduino IDE with a simple blank sketch. And what I do, I'll just go and click on export compiled binary. So, and this will create a hex file, a binary file for the sketch for the selected board. And the board I've selected is a classic Arduino Uno. And here I have an example dashboard, which basically runs in our lab a couple of devices, this Vcon devices. So say this one runs a classic Arduino Nano with the connected OTA shield. So I click on update firmware. I can update both the shield and the host MCU, which is Arduino. I'll just choose the newly compiled binary, which is this one. Blink, start and hex. Click open, and it gets updated. So here it is. It's updated. So you cannot see the board itself. It's in the lab, but basically it started blinking. So this is the way, it's fairly easy way to introduce and retrofit the OTA into your existing project. It could not be necessarily Arduino. It could be like any microcontroller that our firmware supports. So basically, another piece of functionality that we added later on is ability to bridge the Uart interface. So basically, we connected the connectivity chip to the Uart of the target microcontroller, and we can bridge it transparently to any external WebSocket or MQTT server. So basically, imagine you can attach your Arduino output to the AWS IoT, for example. So anything that you print on the remote on the serial console gets to the special topic on AWS IoT, and everything that you send to another topic on the AWS IoT gets pushed and written to the serial on your Arduino. So Arduino might think that it talks to serial, but in fact it talks to MQTT. So that's what this serial bridge is, and it helps to develop this connected kind of products very easily using just serial interface without like a line of networking programming. So and this basically quickly summarize what's the difference between standard approach when one implements OTA in their firmware versus this approach that we've developed where the networking functionality and the firmware update functionality lives on the connectivity chip, in this case on ESP32. So basically, which makes a ESP32 a remote programmer for an external chips. And right now we support several architectures, which is AVR, kind of like a classic Arduino line from Atmel, now Microchip. It supports SAMD, SAMD21 and SAMD51 line, and all lines of STM32. So STM32 0, 1, 3, and 4. So another interesting thing of this is the possibility to implement a remote GDB. So for the ARM-based chips, this firmware, Vcon firmware, implements SWD protocol and gives a RESTful interface to it. So basically, you can use a usual RESTful commands to run SWD commands on the target microcontroller. So it is used right now for reflash the firmware, but it could be used to other things like stopping, resuming a target microcontroller or examining memory. So basically, it's possible to implement remote GDB for the production devices without any fear them like breaking or anything like that. So imagine you have like a fleet of production devices and they behave weird or have bugs, so you can remotely attach to them and use your development environment to fix them and find out what the issue is. So I guess this is it. This was the last slide of my talk. And again, that was vcon.io, the solution for the remote OTA for microcontrollers.
Thanks very much, Sergey. I'm just going to flick to a slightly different screen. So I now appear and everybody can see me. And Tomas will join our meeting shortly. And let me just double check everybody can hear us. Yeah, that's
and
great.
What's the meeting I should join?
No, so you're grand here. So you'll stay here. So
all right, okay,
Tomas will join here. So I guess my first question would be for you. So are 8-bit microcontrollers ever going to go away when people like yourselves are building advanced functionality onto them?
Oh, well, I don't think so, honestly, because like they are very easy kind of to learn. It's a standard traditional kind of learning architecture for many people. So I guess if it's gone away, so it'll be
are 8-bit microcontrollers ever going to go away when people like yourselves are building advanced functionality onto them? Do you want to mute your YouTube page there, Tomas? We're getting a bit of an echo.
They are very easy kind of to learn. It's a standard traditional kind of learning architecture for many people. So I guess if it's gone away, so it'll be.
I'm going to mute Tomas and I'll continue asking Sergey questions, and maybe when I come to Tomas, he'll have his YouTube stream turned off. I guess the next question I'd ask you is, wow, the space station. How does code like that end up there?
Oh, that was an interesting story. So basically, at one point, we've got an inbound request for a license, because we sell Mongoose library as a licensed product. So we've got a request from NASA, and they told us their story. So eventually we sold them, and they told us the story. So the story was that on the ISS, a crew was conducting scientific experiments, but the results of these experiments were collected on the hard disks and like stored on the ISS itself. And every so often, when the mission got a new kind of cargo delivered, they collected physically those disks and moved them down to Earth, right? And basically that means that it was a big delay between getting the data and collecting the data, several months, right? Okay. And they wanted to have like a real-time stream of data, so that's why they were searching for some sort of like a technology connectivity with web interface and web API that allowed them to do that. So they chosen Mongoose a library. So, and that's how it got to the ISS. It was a fun story.
Okay, and just as I'm about to ask Tomas a question, he's disappeared. So I guess I'll ask another one for you. So when you're developing all this software for different architecture types, what sort of lab or test setup must you have? Do you have like devices, different microcontrollers across a room, or?
Yeah, exactly. So basically it's like a big kind of line of breadboards with different like development boards with different micros with the shields attached to them. And when there is a CI running, so every time a new push is happening on the code, they get automatically updated, and like a simple set of tests is run against them. So yeah, if you take a look at that, it's just a line of breadboards with blinking stuff. There are many of them.
Okay, Tomas, a question for you if we have you on sound.
Yeah, I'm working out.
So you were showing a lot of different devices. How did you get access to the actual data? Like, I'm not sure you can go onto your Fitbit app and just pull the data that you require for your research. Did you have an academic license to access it, or how did you go ahead with that?
Okay, yeah, no, that's a very good question, right? We actually used the databases online of photoplethysmographic signals, which is what they are, measured at the wrist. We didn't actually use the Fitbit. In a 15-minute presentation, it'd be too complicated to explain that. So basically, we measured it with another device that uses the same modality. It shines in, green LED at the wrist and picks up the light. If we didn't use the Fitbit, they would not give it. If they would never publish that data, because it would look like junk, right? And you'd be going, how are they measuring heart rate in that situation? And the reality would be, if I guess, is that there's some quite a bit of interpolation going on, put it that way, right?
So we have a question here from Steve for Tomas. Do you have some understanding how the deep learning nets you used solve the problems?
Yeah, it's a great question, because that's a big issue in deep neural networks, is the interpretability or the explainability of their outputs. So in terms of the very initial approach that we used, which was image-based, we were able to leverage also of other people using things like class activation maps and things like that. So there's ways of maybe highlighting where in the image is most discriminative for the class that, like, in this case, the activity of walking, running, jumping, right? And thankfully, when we did that, we could see that it actually was the time series itself. It was actually looking at the plot, right, as opposed to maybe some artifact in the corner of the image or something. But it's a great question. It's a hot topic of research. That.
Okay, I have another question here that's come in for Sergey. When people develop and do these devices, do you get questions about the longevity? Like, will your server still be around in 10 years' time when my device finally needs an update?
No, absolutely. Many people ask that, like a kind of like, okay, guys, how can I be sure that, you're still alive? Well, nobody can tell and guarantee that they'll be still alive. For a kind of a big and serious customers, you always have an answer, like you can give them away the code and the service through the escrow. For example, if you're out of business, it gets automatically transferred to them, so they're not get like kicked out or their service stopped. So. But we are still we are 7 years in business and still are, and have no plans to give up.
That's reassuring. Okay, I have another question here for Tomas. When does it become useless data? After what percentage of fake data that you've inputted? So I guess the question is, when does the data become useless? When it's just all, how much fake data can you put into your program before it loses representation?
No, unlimited, really. It's all based on training. So that last slide I was showing there about producing multi-channel ECG, in that case, it's we trained it on enormous amounts of data, and it can produce arbitrary amounts of it. So that's how that works. So I'm not quite entirely sure. I mean, if you're saying if we kind of cannibalize our own data to retrain it or something, and like how it is going to degrade or something like that.
I'm not sure. I'm sure that's good enough. Sergey, I have another question that's come in for you. Especially, it's around the LoRa networks. And does your code support the really small packet size of the downlink LoRa messages?
Well, yeah, because you see, we use ESP32 as the kind of chosen architecture for the connectivity module, and it has basically supports for everything. It has embedded Bluetooth and Wi-Fi. It has Ethernet controller, and you can attach like any sort of modem, wireless modem, like cellular or LoRa or Sigfox and things like that. But in reality, when you're talking about the firmware update, you're talking about like large files. Sometimes if you might have like several megabytes of size of the firmware, and transferring that through LoRa or Sigfox is something probably you should reconsider your architecture. So the theoretical answer is yes, you can do that, but in practice, I haven't seen anybody doing that.
Okay. And the next question here for Tomas. People are very interested in your background, and was that a sunny backwards Ireland? Or what had you got going on in your talk?
I thought yes, that is a map of Ireland that I have neglected to flip the correct way. But the other than that, the weather is totally not fake. That's an accurate representation of the weather occasionally. I found that map somewhere. Yeah, that's Ireland.
Okay. And another question in here for Tomas is about can you get your papers peer reviewed when they're filled of fake data?
Sure, because one of the we evaluate the performance of our algorithm by comparing it to real data, and there's all sorts of comparison metrics we use to show that this is indistinguishable from real data, or to some degree, while also preserving privacy. That's an interesting thing as well. We need to be able to synthesize human signals, signals from the body, trained on large data sets of actual data, but without any of the data produced being actually too similar to any of the constituent data that we trained it on, because that would then be would have a privacy sort of issue, right?
Okay.
It's not the answer to the question, but people might find that interesting. So there's all sorts of evaluations we do, including privacy checks. That the data is plausible but not identical to anything in the data set has been trained on.
And another one for Tomas. People seem fascinated about you doing experiments while on a plane.
Yeah, that's probably the first time. What was really interesting there is that the processing required for that, this signal processing, wasn't done on the phone. So even smartphones weren't powerful enough for that. It's done on the cloud. So we used Virgin America's crappy. Actually, I'm complaining about getting internet on an airplane flying across the continental US, but we were actually streaming it to our server over a very, very narrow link and doing the processing and the real-time brain state coming back with latency, of course, significant latency. But yeah, that's the world first. That was pretty. It's a bit of a mechanism. It's a very complicated architecture for what we're trying to do, and we probably now just do it on the phone.
Yeah. Okay, and before we leave tonight, do each of you want to say where people can find out more about your work?
Sergey, do you want to go first?
Yeah. So the framework I was talking about could be found on vcon.io, vcon.io.
Okay, and then for us, we're big into reproducible science. So all our papers, we like to do paper and code. So you find our code on GitHub. For that last work, Owen Brophy's, my PhD student, did that last slide that we saw there. It's a good example. So look up his stuff on GitHub, and we do all the papers on archive. Prior to being published in conferences and journals. So yeah, we're big into open access, open science. So Google us. No choice is you find it.
Okay, thanks very much for coming along and speaking tonight for our special Engineers Week NIDA Talks. So thank you very much.
Yep, it's great.
Thank you. Cheers.
Thanks for having us.
And that brings an end to our broadcast. You can visit tog.ie to find out more, and you can also visit engineersireland.ie to find more about the Young Engineers Society. Thanks very much.